A loop of current carrying wire has a magnetic dipole moment of 5 times 10 to the power of negative 4 am squared. The moment initially is aligned with a 0.5 Tesla magnetic field. To rotate the loop so its dipole moment is perpendicular to the field and hold it in that orientation, you must do the work of 2.5 times 10 to the power of negative 4. And the diagram shows 5 possible orientations of a magnetic dipole in a uniform magnetic field B. For which of these is the potential energy the greatest? E. E gear negative x-axis. For a loop of current carrying wire in a uniform magnetic field, the potential energy is a minimum if the loop dipole moment of the loop is in the same direction as the field. The magnetic dipole moment of a current carrying loop of wire is in the positive z direction. If a uniform magnetic field is in a positive x direction, the magnetic torque on the loop is B, is in the positive y direction. Positive y direction. The diagram show 5 possible orientations of a magnetic dipole in a uniform magnetic field B. For which of these does the magnetic have the greatest magnitude? Isn't like the same as this one? Work A. Yeah, it's A. It's from negative y to positive y. Okay, on 47, they're looking for greatest potential energy. And then on that question, they're looking for greatest, magnitude torque. Magnitude torque, it's magnetic torque is an arrow which points upward. Torque potential, it's something which is on the ground. A circular loop of y with a radius of 20 centimeter lies in the xy plane and carries a current of 2 amperes counterclockwise when viewed from a point on the positive z-axis. Its magnetic dipole moment is a 0.25 amperes meter squared in the positive z direction. The magnetic torque exerted on a flat current carrying loop of wire by a uniform magnetic field B is maximum when the plate of the loop is parallel to B, when they are parallel to each other. And then you're facing a loop of wire which carries a clockwise current of 3 and which surround an area of 5.8 times 10 to the power of negative 2 meters squared. The magnetic dipole moment of the loop is C, which is 0.17 amperes meter squared away from you. The units of magnetic dipole moment are C, amperes meter squared. A square loop of wire lies in the plane of the page and carries a current I as shown. There is a uniform magnetic field B parallel to the side MK as indicated. The loop will tend to rotate about PQ with KL coming out of the page, PK, and then KL come out of the page. A current is clockwise around the outside edge of this page and a uniform magnetic field is directed parallel to the page from left to right. If the magnetic force is the only force acting on the page will turn so the right edge moves towards me. Now. A loop of wire carrying a current of 2 is in the shape of a right angle triangle with 2 equal sides, each 15 cm long. A 0.7 Tesla Uniform magnetic field is in the plane of the triangle and is perpendicular to the hypotenuse. The magnetic force on either of the two equal sides has a magnitude of C, 0.15 Newton. Same question, but now we have something magnetic field parallel to the hypotenuse. Therefore, your answer is going to be 0. A ball is at the page. Therefore, this is going to be towards the top of the page. So the diagram shows a straight wire carrying current I in a uniform magnetic field. The magnetic force on the wire is indicated by an arrow, but the magnetic field is not shown. Of the following possibility, the direction of the magnetic field is what? Is E out of the page. The figure shows the motion of electrons in a wire that is near the end pole of a magnet. The wire will be pushed upwards. The diagram shows a straight wire carrying a flow of electrons into the page. The wire is between the poles of a permanent magnet. The direction of the magnetic force exerted on the wire is A. It's going upwards. J&J Thomson experiment involving the motion of an electron beam is mutually perpendicular E and B fields. So it gave the value of what? Of D, of charge or mass ratio for electrons. So a cyclotron, it operates with a given magnetic field at a given frequency. If R denotes the radius of the final orbit, the final particle energy is proportional to what? To C, which is R squared. So I must find the difference between a cyclotron and something. In a certain mass spectrometer, an ion beam passes through a velocity up filter consisting of mutually perpendicular fields E and B. The beam then enters a region of another B magnetic field B to the power of T, perpendicular to the beam. The radius of the curvature of the resulting ion beam is proportional to E, which is E over pi Q. Electrons, and they give me with the mass m and therefore charge negative E are accelerated from rest through a potential difference V and are then reflected by a magnetic field B that is perpendicular to their velocity. The radius of the resulting electron trajectory is C, which is root of 2mv divided by E, and then you divide the whole thing by B. 2mv divided by E and the square root divided by B. The current is from left to right in the conductor shown. Magnetic field is into the page and point S is at a higher potential than point T. The charge carriers are they are positive. An ion with a charge of 3 plus 3,2 times 10 to the power of negative 19 coulombs is in a region where a uniform electric field of 5 times 10 to the power of negative 4 volume divided by m is perpendicular to a uniform magnetic field of 0,8 Tesla. If its acceleration is 0, then its speed is what? Is d 6.3 times 10 to the power 4, same as that one. An electron is traveling in the position x direction. A uniform electric E is in the negative x direction, and in the uniform is approximately So really EI first VI. So the answer is into the page. A uniform magnetic field is in the positive Z direction. Positive charge particle is moving in the positive X direction through the field. The net force on the particle can be made zero by applying the electric field in one direction, negative Y. J2 the positive, but this one you have a negative Y. A charged particle is projected into a region of uniform parallel E and B fields. The force on the particle is B at some angle which is less than 90 degrees with the field lines. So an electron enters a region of uniform perpendicular E and B fields. It's observed that the velocity v of the electron is unaffected. A possible explanation is D. V is perpendicular to both E and B and is a magnitude of E over B. An electron and a proton are both initially moving with the same speed and in the same direction at 90 degrees to the same uniform magnetic field. They experience magnetic forces which are initially equal in magnitude but opposite in direction. An electron is launched with velocity v in a uniform magnetic field. The angle theta between v and p is 0 90 degrees. As a result, the electron follows a helix its velocity vector v, returning to its initial value in a time interval of what? Of a, which is 2 pi m over eb. So re na le sekele e holo se ntho e yatra le sekele nyane se, and then B banyakang. What's the answer? The electron, it travels in a clockwise around the small circle, and proton travels counterclockwise around the larger circle. Okay, but this thing is an eye to the page. A reasonable explanation for this is B. The charge is negative and slowing down. The charge is negative and slowing down. At one instant, it's moving in a positive x direction in a region where there is uniform magnetic field in a positive z direction. When viewed from a point on the positive z axis, its subsequent motion is counterclockwise around a circle in the xy plane. An electron travels due north through a vacuum in a region of uniform magnetic field that is also directed due north. It will be unaffected by the field. At one instant, we have the charge which is negative 1,6 times 10 to the power of negative 19 coulombs, which is moving in the xy plane. The components of its velocity Vx 5 times 10 to the power 5, Vy, which is 3 times 10 to the power 5 meters per second. A magnetic field of 0,8 Tesla is in the positive z direction. At one instant, the magnitude of the magnetic force on the electron is at one instant 3.8. That's 10 to the power of negative 14 Newton. At one instant, an electron of negative 1,6 times 10 to the power negative 19 coulomb is moving in the xy plane. The components of its velocity Vx 5 times 10 to the power 5 meters per second, Vy 3 times 10 to the power 3,8. I think they're repeating the question. Times 10 to the power of negative. An electron, which is whatever thing, is moving at 3 times 10 to the power 5 meters per second in the positive x direction. Right? 8 Tesla is in the positive z direction. The magnetic force on the electron is the 4 times 10 to the power of negative 14 newtons in the positive y direction. A beam of electron is sent horizontally down the axis of a tube to strike a fluorescent screen at the end of the tube. On the way, the electrons encounter a magnetic field directed vertically downward. The spot of the screen will therefore be deflected to the right as seen from the electron source. Hydrogen atom that is lost, its electron is moving east in a region where the magnetic field is directed from south to north. It will be deflected up. UP. Proton charge E traveling the perpendicular to a maximum magnetic field experiences the same force as an alpha particle charge 2e, which is also traveling perpendicular to the same field. The ratio of their speed is c2. A magnetic field cannot change the kinetic field of a charged particle. An electron is moving north in a region where the magnetic field is south. The magnetic force exerted on the electron is A, which is 0. The direction of the magnetic field in a certain region of space is determined by firing a test charge into a region with its velocity in various directions in different trials. The field's direction is A, one of the directions of the velocity when the magnetic force is 0. In where the direction of velocity when the magnetic force is 0. The magnetic field exerts a force on a charged particle if the particle is moving across the field lines. The magnetic force on a charged particle is in the direction of its velocity if never. The magnetic force of a charged particle is never in the direction of the velocity. At any point, the magnetic fields are in the direction of the what? They are never in the direction of anything. So we have this thing. An electron moves in the negative yada. Magnetic force on the electron is what? Is in the negative z direction. In the formula, F is equals to QV times B. Therefore, F must be perpendicular to both V and B. The units of magnetic field might be D, kg over CS.